Hello. In this video, we will discuss what RL circuits are, their components, how they work, and what they are used for. An RL circuit is a resistor-inductor circuit, meaning that it is an electric circuit composed of resistors and inductors driven by a voltage or current source. This means that the main components that you will see in these types of circuits are, of course, resistors and inductors. Simply put, a resistor is a passive electrical component that is used to reduce current flow and is denoted by a zigzag line in circuit diagrams. An easy way to understand how a resistor works is to compare it to a water system where you have a pump that will pump water through pipes, and resistors would be thinner pipes where the current or flow of water is slowed down. It works a similar way in electrical currents. Now, in order to begin to understand how inductors work, we first need to understand how magnetism and current works together. Magnetism is caused by current. So as you have electricity running through wires, magnetic fields will also form around these wires. And in the case of an inductor, you have wires that are wrapped up into coils, which will generate a magnetic field as you have current running through those wires. So all an inductor really is another passive component in an electrical circuit that stores energy in its magnetic field. The buildup of a magnetic field allows inductors to counter the effects of changes in current. As we take a look at an example of an RL circuit, keep in mind some things that may help you understand how inductors work. First, try to remember that they don't like change. Once they've built up a magnetic field, they want to remain the same, even when current may increase or decrease. When current increases, they try to stop it with an opposing force. When current decreases, they try to stop it by pushing electrons out to try to keep it the same as it was from before. And if the circuit shuts off entirely, the magnetic field will convert to current until it runs out. This means that the current through an inductor cannot be turned on or off instantly. As we take a look at our circuit diagram, we can see that we have a complete circuit that will start from the battery, flow through a resistor, denoted by the jagged line, and then through an inductor, which is denoted by the swirly line, and then all the way back to the negative terminal of the battery. As the current flows through the resistor and then to the inductor, it will be first met with an electromotive opposing force that it will have to overcome first in order to start to build a magnetic field. And once this electromotive force is overcome, the current will flow through the inductor as normal, with the magnetic field reaching the highest strength it can according to that current. Now, if I were to turn the switch so that the voltage source, or current source in this case, was not connected to the circuit, the magnetic field that was built up by the inductor will now drive current and keep the current going through the resistor for a little bit longer until the magnetic field dies down. This is the principle of inductance that allows this to happen, for the current to continue in the absence of the main current driving force. Now that we have a basic understanding of how inductors work and how RL circuits work, let's take a look at how they are used in our everyday lives. So they are used to boost converters to increase the DC output voltage while decreasing current. They can also be used to choke an AC supply and only allow direct current to pass. We can use them to filter and separate different frequencies of current, and they are also used in transformers, motors, and relays, and many other electrical components. One thing that you can keep in mind is that every tightly coiled wire will act as an inductor. So this will include motors, transformers, and relays. One last thing that's important to understand about inductance is how we measure it. So inductance is measured in the unit of the Henry. 1 Henry equals 1 volt of EMF across the inductor with 1 ampere of current. So this means that the larger number of Henrys you have, the higher your inductance is. And the higher the inductance that you have, the more energy that can be stored in the inductor, and the more energy it can provide through its magnetic field.